I was asked to do a presentation. This was my date, January 6, 2022. And I was asked to do a presentation on loop antennas. My name is Paul Racine, Kilo Bravo Zero Papa, KB0P, and I'm located in Green Bay, Wisconsin. I've been a ham since 1984, so I've been playing around with this stuff for a while. I am not an expert or a professional. I'm not a professional antenna builder, but so I'm just doing this presentation to help you guys learn what I've been doing and share some of my experiments with you. Beep. Okay, this presentation is not about hula hoops. It's about loop antennas. The objective of this presentation is to provide a brief introduction to loop antennas. At the end of this presentation, you will be able to define the difference or define the difference between a small loop antenna and a large loop antenna. So I'm going to review both of those. You would be able to, after this presentation, you will be able to list the advantages and disadvantages of the small loop antenna. And you'll be able to navigate the internet to download instructions to build your very own small loop antenna. This presentation, the outline, I'm going to go over a brief history of loop antennas, very brief. We're going to talk about the components of a radio wave. We're going to discuss what is a loop antenna, and I'm going to just review very quickly a large loop antenna and a small loop antenna. We're going to go over the radiation pattern of both types of antennas. And then we're going to talk about receiving small loop antennas. That's what this presentation is mostly about, is the receiving small loop antenna. I'm going to show you quickly what's on the market. There is so much on the market, but I'm only going to show you a couple examples. And then finally, at the end, we're going to give you some instructions on how you can build your very own loop antenna. And I'll give you some web pages too. So a little bit of history. So Scottish scientist James Clerk Maxwell, he was developed a scientific theory in the 1860s, which related the electromagnetic waves. And he defined electromagnetic waves by defining them as a combination of electrical waves and magnetic waves. And that's what we're going to talk about here. And he may have roasted coffee at home as a hobby on the side. So this could very possibly be, and I believe it really is, the first loop antenna that was developed, 1886. So Hertz did an experiment to prove Maxwell's theory. So what he did is based on, he took a loop antenna. You can see a picture of the loop antenna here. This is actually set up in a museum. And you can see he has a spark gap transmitter. I don't know if you guys can see my mouse or not. Are you able to see that? Somebody shake their head. Okay. So this is the spark gap transmitter. Now remember, this is 1886, so things were pretty crude back then. So we got our little coil here, and we're generating a signal, and we're creating a spark. And these toilet bowl plunger looking things here, these are the antennas, the transmitting antenna. And then we had a receiving loop, which is completely passive. It's over here all by itself on an insulated pole. And there was a little spark gap at the end of that loop antenna. There's two balls here, if you can see that. And what happened is when that spark was generated, the spark jumped over and was received by this loop. And that was an introduction, or not an introduction, a presentation to show how radio waves, electromechanical or electrical waves and magnetic waves travel through the air without any electrical connections. So this very well could have been the first loop antenna at the time. Now, based on the measurements of these devices, scientists have determined that the frequency that was being used at the time, which I thought was really interesting, based on the size of the components, was around 50 megahertz. So that's pretty neat. This first experiment was in the VHF band. This is a schematic of that circuit. You can see here the antenna is just a loop. It's not a complete loop. It's has an open gap here. and then our transmitter was a ignition coil. So it was a coil that produced a spark, and then that spark was transmitted from point A to point B. So I thought that was pretty interesting. That's probably one of the first antennas that was produced, and it was a loop antenna. So Maxwell's theory was that the electromagnetic wave, or radio wave as we know it today, consists of two parts, an electrical component and a mechanical or magnetic component. All right. So traditional antennas, and when we think of traditional antennas as ham radio operators, we're referring to like a dipole antenna that has two elements. And a traditional antenna will respond to the electrical portion of a radio wave. Now, what's interesting is a lot of the man-made noise that we experience in our homes or in our businesses are also in the electrical part of the wave is generated in the electrical part of the wave as well. So a lot of our antennas will pick up that electrical noise. Now, there's another part of the electromechanical magnetic wave, and that is the magnetic part. Now, a small loop antenna responds to a magnetic portion of the radio wave. And since the electrical noise doesn't really reside heavily in that area due to induction and close by objects, the small loop antenna actually is an excellent receiving antenna that would be used to receive signals in a noisy environment. So that is one of the advantages of a small loop antenna. And we'll talk about that here in a little bit. So you can see this representation here. We have our electrical component and we have our magnetic component, and you can see they're out of phase with each other, different angles. You can see our antenna here, and that signal just goes out, and you can see the two portions of the wave as it's radiated out in a given direction. All right. So what is a loop antenna? So a loop antenna is an antenna that consists of a loop, basically a coil of wire. That's all it is, just one big coil of wire. And I have here in this slide, you can see there's a large loop and there's a small loop. So those are both loop antennas, but obviously they're different size. So this small loop, if you can see this here, we have our house, we have our shack in our house, and this loop could be the entire perimeter of your yard, for example. It's quite large. It consists of 4 sides. And if this was a 80-meter loop, for example, tuned for 80 meters, the whole length of this whole antenna would be 272 feet long. Well, that's quite a bit different than a small loop like this that might only have maybe 6 feet of conductor from here all the way around and back to here again. So this might have a 3 to 4 foot diameter. So much difference in physical characteristics. And they operate differently too as a result. So again, what is a loop antenna? It's basically just a coil, a loop of wire. So what shape can I make a loop antenna? Well, you can make it any shape you want. Whatever your area. If you have a yard that's square and you have supports in the corners of your yard, you can make a square loop. You can make a triangle loop, circle, anything you want. Commonly, if you have a triangle loop, those are known as delta loops. Then you have your circular loops, and you have your quads or your square loops, diamond shape, just anything. So whatever your area happens to, whatever support, everybody's yards are going to be different. You're going to have different supports. So you can make a loop, you could basically wrap your loop around your house if you'd like to do that along the perimeter of your house. All right, so we're just going to talk about the large loop first. So the large loop is large, and that is large based on wavelength. So when we talk about size, we're talking about in comparison to wavelength at the frequency that it's cut for. So generally a large loop is nearly equal to 1 wavelength total. So an entire wavelength on 80 meters is about 272 feet. Entire wavelength on 40 meters, which is 7 megahertz, is about 142 feet. So how would you build something like this? You would take that entire wavelength, 142 feet, divided by 4 if you want to make it perfectly square, and then each side of that square is going to be a quarter wavelength. When you add all that together, it's going to be a total wavelength and size. A large loop antenna is known as a resonant loop. Why? Because it is actually resonant at the frequency that it's cut for. A large loop has high radiation efficiency, so it propagates very well, gets out, people can hear you. And what's interesting is a large loop will radiate at right angles. Now, that's going to change a little bit. Things will change as you raise the height of a loop, and then you start developing lobes. But we'll talk about that in the next slide or two here. And I'll show you what I mean by it radiates in right angles to the antenna plane. So in this case here, if you can imagine this loop hovering above your house, it's flat. Okay, so the plane of the antenna is flat. It's over the top of your house. So when I say the loop radiates at 90 degrees, it's radiating straight up. So 90 degrees, or at right angles to the antenna plane. So this loop antenna, for example, would be radiating straight up. So it would be like looking through, kind of like looking through a magnifying glass, and as you're looking through that glass, that is the direction that the signal is going. And unfortunately, a large loop antenna responds largely to the electrical portion of the radio wave. Why? Because it's a resonant antenna, it's large, and it actually does respond to the electrical portion of the wave. So even though it's a square loop, it's a complete circuit, a dead short, if you will, from ground to hot on your coax, it does largely respond to the electrical portion of the wave. And like I mentioned earlier, that's where a lot of the interference, man-made noise resides. And because it responds to the electrical portion of the radio wave, it also couples itself to other metal objects in the area. And that's why you pick up, extra noise and different things like that. All right, so now this is a small loop. So you can see physically it's much smaller. And a small loop is, again, based on the wavelength. So it's a fraction of a wavelength, maybe 1/10 of a wavelength or something very small. So for instance, an 80-meter loop, a full wave loop would be 272 feet. And maybe an 80-meter small loop used for receiving 80 meters might be 1/10 of that. Might only be, 20 feet or something like that. Very small as far as wavelength is concerned. A small loop is known as a magnetic loop antenna because of its small size. The voltage is very low on the loop, around the loop. And because of that, the loop tends to respond more to the magnetic portion of the radio wave. And that's one of the advantages actually for receiving. It has a low radiation efficiency. So in other words, when you transmit on a small loop, we're not talking about transmitting loops in this presentation. We're actually talking about receiving loops. But a loop will have a low radiation efficiency. So if you were to use a loop to transmit, your signal will not propagate as well as compared to using a large loop. So the efficiency is considerably lower. What's interesting is the receive pattern is perpendicular to the antenna plane. And we'll show this here in the next slide, which is different than the large loop. And just like I mentioned already, the small loop antenna responds to the magnetic portion of the radio wave. Now, small loop too, if you want to get a little bit technical, and I don't want to get too technical into this, but because the voltage is relatively low around a small loop, because basically it's a dead short circuit, ignoring this capacitor up here in this photograph. So then the voltage is relatively low, and because of that, the coupling, the coupling of this loop antenna will not couple as easily to nearby objects. So that's another reason why they generally are quiet antennas for receiving. Okay, so this is just a quick little drawing showing the radiation pattern of a large loop versus a small loop. So if you have a large loop antenna, basically that is a cloud warmer. So you can see you're shooting your signal straight up. It'd be just like having a mirror on your ceiling. and you shoot your flashlight straight up at that mirror, and it's going to come right back and hit you in the face. So a large loop antenna like this, relatively close to the ground based on wavelength again, because when we talk about size, we're talking based on wavelength. This antenna is going to radiate straight out and come back straight down. And as a result, it'd be good for talking locally on HF. As you raise this loop above the surface of the ground and get it up higher and higher and higher, eventually lobes will start to develop off to the side of this antenna, and it'll start becoming more, it'll radiate more at an angle. But most hams practically can't get an antenna really super high in their yard. Most hams. So from a wavelength point of view, again, our antennas are, especially on 80 meters or 160, our antennas are very close to the ground. Now, when you look at a small loop, this little man here is holding a small loop, it radiates off the sides. So if you were using a small loop for receiving, the signal's not coming through here. In other words, as I look through the center of this loop, that is not the direction that the signal's coming from. It's actually coming from the side. So what's nice about a small receiving loop, you can use it for direction finding, kind of, sort of. You know, it's two directions, but you can kind of use it for direction finding. And also, if you have noise straight behind me here, and if I turn the loop like this, that noise that's coming from behind, if you can imagine that, is nulled out, or it's very low in signal strength, because my loop is actually pointed east and west right here. Okay. So you can rotate these loops and actually, you know, increase the signal strength of whatever you're listening to, depending on what direction it's coming from. An example I'm thinking of here is like AM broadcast stations. These things are great for AM broadcast receiving, because you can turn the loop, and because several stations share the same frequency on AM broadcast, for example, you can null out one station and receive another station and favor that station based on whatever direction it's coming from. So that is one of the advantages of a small loop. Beep. So again, just to, as a reminder, our focus in this presentation is just on small loop antennas. So we're just going to be talking about receiving loops, and that's it. And how this whole thing came about is I started playing around with a receiving loop, and I was building one, and I was showing Dave my antenna, and he says, hey, we should do a presentation on this. So again, I'm not getting really technical here, but I'm just trying to whet your appetite so you can start doing some experimenting on your own. So let's talk about this again. What are the small loop antenna? What are the advantages? It's small, it's compact, it's portable, it's economical, it's easy to build, simple construction. It's great for apartment dwellers or somebody who wants to kind of hide from the neighbors. It does not require a ground. It's a relatively low noise receiving antenna, meaning that it will not pick up as much static. And it's directional, and that can be an advantage or a disadvantage. The disadvantage of a loop is its poor efficiency. It's very poor efficient antenna, either transmit or receive, because you don't have a lot of surface area. You don't have a lot of metal. So in order to make this a good receiving antenna, usually you have to put a preamp or some sort of amplifier in this portion of the antenna to boost the signal that you're receiving. So it requires a preamp. Requires impedance matching, because it's such a short length of conductor and it's basically shorted. It's going to have a very low impedance. So we have to get that impedance, bump that impedance back up so it matches our radios. And again, it's directional. Again, that could be a disadvantage or an advantage. Beep. So we're getting to see what's out on the internet. You can do a search on receiving loops and you can find tons of stuff. So here's a couple of examples I pulled out from the internet. You could order the ALT 930 and pay $9,000 for this antenna so you can listen to your favorite broadcast station on shortwave. And this loop is good up to from 2 megs. Let's see, it looks like a 30 megahertz loop antenna. So basically HF. Or you could spend $550 from DX Engineering and get this antenna. This is an excellent antenna. So who has $550 laying around, or who has $9,000 laying around and, you know, can just buy this antenna and use it? And I certainly don't. So there's many excellent options out here, and there are some cheaper options out here too, but I just picked these two because this is a popular receiving antenna here. And this one was a little bit ridiculously priced, so I had to put that on here. But we're going to talk about building our own loop antenna. So what do we need? Well, we need some tools. We need some copper tubing, possibly wire, coax, PVC pipe. So all this stuff is locally available. You can use cable TV coax if you want. That's really cheap at hardware stores. PVC pipe is plentiful and easy to work with. Wire, we all have wire laying around. So you can actually build your own loop antenna very easily. So what I have showing next is I have two examples of homemade loop antennas. This first antenna is a do-it-yourself. It's a noise canceling passive loop. Now, when I say passive, what do I mean? Well, what I mean is there's no active component in the antenna. It's basically dead. So there's no preamp. It's just a piece of wire. That's it. There's no preamp. It covers the low frequency band up to HF. So it's a great antenna for receiving low noise reception of low frequency. And when I say low frequency, I'm referring to the band that's below the AM broadcast band. So it'll work well up through the AM broadcast band into 4 megahertz, 7 megahertz, and, you know, maybe up to 20 meters. And this antenna is actually designed around and is similar to the commercial AirSpy U-loop, but you can build it yourself. And how do you build it? It's just a piece of coax and a balun. So you'd have to wind this balun. So remember earlier I had mentioned that loops are basically a dead short circuit of a short piece of wire. In this case, we're going to use a piece of coax as our wire. Well, in order to get that really low impedance, because a dead short is zero impedance. So in order to get that impedance up so it matches our radio, we have to build a little balun, a little transformer to convert that low impedance up to a little bit higher impedance so we don't short out the antenna connector on our radio. So to build this antenna, all you need is a piece of coax and a little balun circuit. And if we go to this website here, this website will actually show us how to do that, and we can look at that afterwards. This is what the website's showing. It is almost the exact replica of the commercial antenna that I mentioned earlier that's available. And this is what the bill of materials is right here for that antenna. The only thing you would have to maybe purchase if you don't have anything similar to this laying around is you might have to buy this balun, the ferrite core, to wind that transformer on. And that ferrite core, by the way, looks like a set of binoculars. That's the only way I can describe it. It looks like it's a ferrite balun, but it looks like a set of binoculars. But you can use anything you have laying around. You don't have to stay exactly with this. You know, you can experiment. As hams, that's what we do. All right. So this is the passive version. This antenna here has, with the instructions online, which we're going to look at here in a little bit, this antenna is tuned and seems to work best around 4 megahertz, which is 80 meters. So this is a great receiving antenna for 80 meters. And then as you go higher up in the HF band, get closer to 10 meters, which is around 30 megahertz, it drops off very quickly. But it does also receive the AM broadcast band 160 very well, and it receives the low frequency band, which is in our ham bands, which is around 470 megahertz or kilohertz, 470 kilohertz, below the AM broadcast band. And that's where a lot of our noise is anyway. A lot of our electrical noise is in that spectrum. And this antenna makes an excellent receiving antenna for that because it helps eliminate that electrical noise. All right, simple active receiving antenna. So the antenna we just talked about was passive. In other words, it didn't have any preamps in it, but we can also build an antenna that has a preamp in it to boost our receive signal. So that antenna, the active receiving antenna, is an antenna that I built. It can be built from hardware store components, Menards, Home Depot, wherever your favorite hardware store is. This type of antenna requires a preamp, so an amplifier, and an impedance matcher. So it has a preamp and a little bellin built into it. So now you're gonna have to start digging into your parts bin, you know, for some transistors, capacitors, resistors, different things like that. And because it's an active preamp, it needs power to function the amplifier inside. This here is the web page. Again, we're going to go into that and I'll show you where that is, or you can just search it on your own. We'll go over that during our discussion afterwards, open discussion. And the plans are all online. So here's an example of one of those antennas that I started building. So what I did is I went down to the local hardware store and I bought a 6 foot, I believe it was 6 feet, a 6 foot piece of aluminum strap. Now, our local hardware store here, I have a Home Depot and also a Menards. Now, I don't know if there's any Menards on the East Coast or not, but they're really, there's quite a bit here in the Midwest. So I went and bought an electrical junction box, some stainless hardware, and I bought this aluminum strap. Now, they have different widths. I bought an 1.5 inch wide, but they have 1 inch wide strap. So, and the reason I did the aluminum, because I figured it was a larger surface area, it was light, and it just looked kind of cool. So that's why I went with that. So how did I fasten this straight 6 foot piece of aluminum onto this box? Now, I did not bend this. This is just naturally bent from being mounted on this box. So what I did is I measured up on each end of my aluminum strap and I put it in the vise and I carefully bent it so I had a nice clean bend. Drilled a couple holes equally spaced. And I just bolted the aluminum to the electrical junction box. That's all I did. And did that on both sides. Looped it around, bolted it in, and it took that natural shape. It's free. It's not supported by anything. It's just sitting there, just like that. Now the circuit inside, this is what the circuit inside is going to look like. So you can build this many different ways, but you can see where the bolt holes come through for the mounting bolts for mounting the aluminum on the outside. And then you can see I have a little circuit board in here, picture of a circuit board in here, and you can see the components are soldered to that ground plane. This is called dead bug style. It's not really critical because this is being built for HF. So this isn't super critical. You can use dead bug style. You could put it on a printed circuit board. You can put it on perf board, whatever you want. Just using junk parts laying around in your junk box. I have a ton of these core little donuts, these Ferrite donuts from years and years ago, all categorized in little drawers. You know, some hams may not have those, so you may have to purchase something like that to wind your ballon. And here's the ballon. It's real tiny inside. And then there's an SO239 mounted on the bottom of the box for plugging your coax in. So one of the things I mentioned earlier, okay, that's fine and dandy. I got a preamp circuit at my antenna. My antenna is remotely mounted, say in your attic or on a tree or sitting on a pole out in your backyard. How in the world do I get power out to that antenna? Do I have to run a separate power wire besides my coax? Well, you could if you wanted to. Or you can send the power or the DC voltage that powers the circuit right down that same coax that's sending the signal down to your radio. Well, how do I do that? We're going to talk about a injection unit. So when you send power down a coax to power a remote circuit, that's sometimes known as phantom power. This here is a circuit from online. This is what the circuit looks like if you were to build this. It gives you the schematic and the components that are needed. And this schematic is showing two separate connections, your received connection on this box and a power connection. But you can actually eliminate this circuit right here, and both power and receive can come down into the circuit over here. So there are different designs on the internet. So when you build this, be careful, make sure you build, you know, the right one here, and you can see this is the power unit right here, remotely, I'm sorry. This is the power unit that's remotely mounted in your shack. Here's the coax going to the antenna, could be 50 feet long, 100 feet long, whatever. And both that DC voltage, 12 volts, and the received signal are coming down the center conductor, your coax, and feeding the circuit over here and powering these transistors. All right. So what do I use for a powering unit? Well, there's a couple options. You can either build the circuit like I was just showing you and stick it in a piece of PVC or a metal box or whatever, and that's going to be mounted in your shack. You would hook it to your 12-volt power supply. Or you can buy one of these bias tees. I have one of these. It's an MFJ device. And how this works is there's a terminal on the bottom here. You can't quite see. It's over here. There's a little plug over here on the side. You can't quite see. But it hooks to your power supply. So you're injecting 12 volts into this thing. There's a switch for turning it on and off. It's currently in the off position. This connector up here goes to your antenna, goes to your remote antenna. And this connector here goes to your radio. So when you flip the switch on, you're sending 12 volts out to your antenna. And that's how that circuit is powered. And again, you can build these all day long in a small piece of PVC or a little metal tube or whatever you want. Okay, you just need some components. You need some chokes, a couple capacitors. All right. Or if you're not quite comfortable with building either this, you know, with the active preamp, and you try the passive loop and you don't like how it performs, but you want something that's going to have an amplifier in it, but you're not super comfortable with building this amplifier, here's another suggestion, and I highly recommend this suggestion. This is the MA30 Loop. I have one of these. It works great. The first one I had did not work great. It actually was burned out right out of the package. But I returned it. They credited me and gave me a new one. They sent me a new one, and that one works great. So how does that work? This works exactly like this, except instead of having an aluminum strap, it's made out of a piece of thin steel wire. And you can see that right here. It comes with a piece of wire rolled up in the box, a small short chunk of mini coax. This is 174. This is really tiny, tiny coax. And this, I would say, is at least 30 feet long. That's a lot of tiny coax. Comes with a little USB dongle. And this is our power injection box right here. So what you do is you unwrap this thing. Comes with a couple screws. You can get a piece of PVC pipe like this here in this picture. You mount this preamp. This is the preamp circuit. You mount that preamp on the PVC pipe. You string around this loop, and when you unspring this, it takes the natural form of a circle, and you connect that on with these wing nuts here, one on each end. And the whole reason for this PVC pipe is just to keep it formed so it doesn't cave in on you, because this is really skinny wire. You run that coax into your shack, plug one end into this power device. It says antenna on here. The other end, the jumper, the output of this goes to your receiver. And then you use this USB port that plugs into here to provide 12 or 5 volts of power to this device, which powers up the preamp. And that is an excellent receiving antenna. It's about 50 bucks. You know, you can see it in different prices, but it varies. But it's averaging around $50 on Amazon. It covers 0.1, which is below the AM broadcast band, 0.1 up to 30 megahertz, and it works quite well. I've been using it now for a while. It's small, it's lightweight, it's somewhat invisible. You can't really see it. You can see the PVC more than you can see the antenna. And it's a quick way to get listening right away. And no building, you know, you don't need to construct anything. So in conclusion, since the first loop antenna in 1886, we've come a long way. Okay, that's it. And thank you for your attention. And now we can open up our mics, have questions and discussions. And I may not be able to answer all the questions, but we'll just talk about what we saw and if anybody's interested in anything like that. So, and if anybody else has any experience, please jump in and talk about it. And that's it. Over to you. Who's the host here? Is it Dave or is it Dick?
It's not me. I think it's.
Oh, I don't know. I mean, anybody's got a question, just ask it. And
Okay, I'm gonna unshare because I'm gonna switch to the web page. Oh, did you already unshare for me?
I unshared for you.
Okay.
Looks like we have a question in the chat.
Okay, let me take a look. No, from what I experienced, so the question was, if we have a small receiving loop, is you know, and how we talked about the direction of the signal that's received through the receiving loop. So can you guys see my camera?
Yes.
I'll use this
yes, we can.
magnifying glass. Okay. So let me grab a pen here. So say this is my loop, the black part, not the glass, but the black part. The signal is going to be received off to the side here and off to this side. It's not received this way and it's not receiving this way. So the question was, does this side of the antenna have a null compared to this side? And I haven't found that to be the case. So if I'm receiving a station from, say, Chicago, and I'm in Green Bay, Wisconsin, so Chicago's south of me, I would have to turn my antenna so it's facing north and south in order to pick up that station. I can pick it up like this, but when I turn my antenna like this, it gets much, much, much stronger. Now, do I know if that signal's coming from the south or the north? No, because it's receiving off both sides. But I just know where Chicago is. And if I spin my antenna east to west, I will pick up east to west signals better. So that's what I found with mine. So what you could do with these antennas, you could put them on a little TV rotor and you can rotate those. And you can do that. People do that. So same thing on 80 meters. I've rotated my antenna on 80 meters just for a test. And I found that it actually gets stronger if I rotate it toward the station I'm receiving. So that's how these can be used, kind of sort of like direction finding antennas. It's really neat.
Interesting. Oh. Yeah, I just want to say I have one of those MLA-30 loops. Actually, it's right in front of the house. And I have a shortwave. I have a Hamlin. And that's what I'm using as my my shortwave antenna right now. And that thing works pretty well on shortwave.
Yep. I was surprised when I got my first one and it didn't work. I was thinking,
Oh.
oh, great. What a piece of junk.
Yeah.
And I started reading reviews on them and everybody had excellent reviews. And I thought, well, how can that be? Well, so I wrote the company on Amazon. That's why I like ordering stuff on Amazon. They
Me too.
refunded my money right away. I returned it
Mhm.
and I got a new one. They replaced it and that one worked great. So it's
And
very
another-
possible the one that I got the first time might have been a return. Because that
Oh,
does
okay.
happen. Yeah.
Another message in the chat box, Paul.
Oh, yeah.
Oops. If you look at, so the question was, do you think that this type of antenna was used for radio direction finding in the old days? So I remember a movie, and I remember when I was on CB back in 1983, I was just a kid then. I didn't even know what ham radio was. That's how I met a ham radio operator, was on CB. But I remember I was all interested in that, and I was watching these goofy movies, and they actually have a loop antenna for direction finding on CB. It's on the HF frequencies. Oh, Ross is must be on HF or something. I heard a lot of interference. So they can be used for direction finding, and if you look up online, you can actually do fox hunting on 80 meters using a loop antenna. If you look up 80 meter or HF fox hunting, there's actually antennas out there, and they're loop antennas for direction finding.
Paul, do you think the band material that you used initially on that first one versus the wire, is there any difference? You know, usually rule of thumb is bandwidth for surface area.
Okay, so here's what's going to happen. So you think the bigger the surface area, the better the receiving is going to be, right? Because I have more metal out in the atmosphere, correct?
Oh, I'm
So
thinking,
surface
I was
area.
thinking bandwidth, but
Yeah, and that'll increase bandwidth too, but here's what happens. So you think, okay, bigger, better, right? So then you put a bigger loop on it, wider bandwidth, wider strap. It increases the bandwidth and decreases the inductance because it's flat and it's wider. But what's going to happen is you will increase your receive signal, but it gets to the point where you're increasing your receive signal so much you overload the amplifier. And when you start overloading the amplifier starts producing, bad effects, and that it starts to clip basically the amplifier, and that clipping goes into your receiver, and it starts producing all these poor, harmonics and different things like that. Or another thing that could happen is the signal could be so good, so strong, and your amplifier and your antenna can handle that extra signal, but then you end up overrunning your front end on your receiver. And what happens is you could be on 10 meters, using that to receive on 10 meters, and all of a sudden you're picking up your local AM radio station on 10 meters. That's a good indication that you're overloading that amplifier, because now it's starting to spew all that broadcast stations all over the spectrum, and you're receiving stations where they don't really belong. And that's a good indication that it's too strong. So that's why you don't want to go too big, but it does increase the sensitivity, and it will increase the bandwidth. Yes.
one other follow-up question to that. Did you ever use an AB switch on the receiver for
Not yet.
noise back and forth?
Well, I used my dipole.
Is it indeed a low noise antenna?
Yeah, so I used my dipole and I compared it to that, but I don't know if that's a fair comparison. Of course, the signals are stronger on the dipole, but if I were to close my eyes and flip the switch, there are some cases where I can hear the signal better on the loop. It may not be as strong as on the dipole, but I'm not pulling in the extra noise either. So what you're listening for is that signal to noise ratio, the noise compared to the signal itself. And there are cases where I can receive signals better on the dipole where I don't receive them very well on the loop. So it's not perfect, but it does seem to be a quieter antenna because it's not picking up the noise as much. But I also found that it doesn't pick up the super weak signals either because it is so small.
Paul, can I ask a question?
Pardon me?
Paul, can I ask a question?
Yeah.
The wire thickness, does it make a difference? And the coax, what type of feed line do you use?
So the purchased antenna I have, that one I showed you, is RG174, which is really, 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 really tiny. So the resistance per foot is super high. There's a lot of impedance. So what happens is the signal decreases as it goes through the coax, and by the time it gets to your receiver, it's considerably lower. But if the preamp is doing what it's supposed to do, it's amplifying that signal before it sends it down that coax, that's usually not going to be a problem on HF frequencies.
Okay.
But I would prefer to use RG8X because it's light and quite manageable. But I found I used, because it's so cheap and readily available, is 75 ohm cable TV, closed circuit TV
Okay.
coax. And that works really well. Because usually that stuff, when you buy it, it's double shielded and it doesn't cost that much. And I've even used that on HF as my transmit coax, and I've had good luck with it.
Does the thickness of the wire make a difference if you put up a loop?
It's going to increase. So what happens if you're using a round piece of wire compared to a metal strap? The flatter the wire, if you're using strap, it's less inductance per foot, or per inch, maybe, if you want to think of it that way, because it's not super long. So it does improve the efficiency, but again, it's such a small loop anyway. I think that antenna that I bought that has a really skinny wire, I'm going to eventually move that into a separate box, separate junction box, and I'm going to put strap on it to make it better. So I think it does, but For experimenting, I don't think it makes that much of a difference from an experimenting point of view. You might
Nicholas
just-
has a,
Oh, go ahead.
I'm
Oh,
sorry, Nicholas has a question in the chat box.
So if you can only receive on the loop north to south and miss anything coming east to west, can you add another loop? Yes. So there's a plan. So the question is, if I have a loop, where's my magnifying glass? If I have a loop that's fixed, that's not on a rotor, and it's east and west sitting in my yard, I'm going to miss some of the signals, the weaker signals especially, that are north and south. So if you look online, there's actually a dual loop where you have two loops, one loop going this way and then the other loop going this way. And it looks like a little egg beater. And I found the plans for that. And I thought that is a neat thing. So now you're receiving signals both north and south and east and west, if you're planning on just using it for a general receiving antenna. But what's nice about these loops is if you start your vacuum cleaner, I mean, I'm just being ridiculous here, but you start your vacuum cleaner. That used to wipe out our channel 3 on TV when I was a kid. Start the vacuum cleaner and all of a sudden channel 3 would go goofy. But if you start your vacuum cleaner and create a nice static generator in your house and then go down to your radio, just leave your vacuum cleaner on, somebody will think you're cleaning. And then go down to your shack and then rotate that antenna if you have a way of doing that. And you'll notice vacuum cleaner comes in strong, vacuum cleaner comes in weak. So you could actually direction find your vacuum cleaner.
Paul, I've got a couple of questions.
Oh, go ahead, Andy. Yeah.
What happens if you squeeze this thing into an oval or some other shape?
Yeah, and you can experiment with that. I guess round, because when you do the area, you know, I think when you do the math and figure out what the area inside the circle is, I think circle is the most efficient because that's the biggest area, I believe. And if you use square and you start calculating the area inside a square, it's going to be not as, you know, and then you could squish it. But now what's going to happen if you start squishing it, it's going to look more like a folded dipole now. And then the wire at the top is going to come close to the wire at the bottom, and that's going to start changing the impedance of the whole thing and the characteristics of the whole thing. And it might even start looking like a small dipole at that point.
The second question I have is, could you phase these things like on a Yagi, put 1 or 2 or 3 together to change it or make it more directional in a specific direction?
Yeah, I wonder, I never experiment with that, but that's when you look at the receiving antenna or the transmitting and receiving antennas for satellites. I built an egg beater antenna. I want to rebuild it now because I'm going to use one of these electrical junction boxes. I'm going to use that strap that I got from the hardware store, but I just did it with coat hanger. And that's kind of what you're doing there. You have 2 loops that are like this. One's this way and one's this way. And you phase them together. And when you start doing that, you start creating circular polarization. So, but I'm not sure how that would look on HF. I never experimented with that on HF, so I don't know. But yeah, I could imagine you could try that and see what happens.
Thanks.
Interesting.
So if you phase an antenna, like you have 2 loops and you phase one 90 degrees out the other, how do you do it 90 degrees? You take 90 degrees piece of coax, which is a 1/4 wavelength. So you build one antenna, you build a second antenna, you know, one this way, and then you run your coax to one, and then you run a 1/4 wave jumper to the other one. And now you just phased them 90 degrees out of phase, and that becomes a circular polarized antenna.
Interesting. Do we still have the Oscar satellite up there?
Well, there's a ton of satellites up there,
Okay.
but there's one Oscar satellite that was put up because I was playing with them last year. There's one satellite that was put up. When was it? In the 70s or something? And it went dead because what happens is the batteries go dead on these things, and they're still floating around up there, but they stop transmitting because the batteries go dead. And some of them will come back to life when the solar panels hit the sun, and then they die again when it goes into the dark. You know, that's a great indication that the battery's shot.
Yeah.
But some of that, I think one of the Oscars actually came back to life. And people are working it.
Well, the reason why I asked that question is because back in the day, when I first got my license about 40 years ago, I used to use a circular polarization antenna on I think VHF to hit the satellite.
Yeah.
And there was a relay that you had hooked up to it too. So you can do left-handed polarization or right-handed polarization by toggling that relay.
Yep.
Yeah. Mhm.
So what's happening there is you're changing your phasing stub
Yes.
from one loop or to the other loop, and you can make it left or right depending on which one you phase first.
Yes.
So I did something in college. I had 2 magnet mount antennas on my car. Identical. What brand were they? They were the Fisher Price brand. Cheap ones back then in the 80s that were pretty cheap. Anyway, 5/8 waves, and I stuck them on the roof of my car. I think a half wavelength apart. Yeah, half wavelength apart. So on 2 meters, that's roughly, I don't know, 38 inches or something like that. And then the coax coming out the antennas were exactly the same length because they're the same antennas. And then in the back seat, I had an antenna switch, and I put a quarter wave. Was it quarter wave or half wave? I can't remember, but I put a stub on there so I could switch that stub over to the front antenna. So basically the stub was in series with the coax to the front antenna or to the back antenna. So as I'm driving down the road, I can beam most of my 2 meter signal to the front of me. Or if I flip that switch, I can beam most of my signal to the rear of me, depending on where the repeater was, that I was driving toward the repeater or away from the repeater. And that actually worked.
I had a friend of mine, KA2ZEV, many years ago. He had a directional finder in his car, and he had 4 antennas on his car. It looked silly, but he had one in the front, one in the rear, and one in the left, and one in the right. They were like they looked like the handy talkie antennas, you know, those
Yeah.
type of like stub antennas.
Rubber duckies, yeah.
Yeah.
MFJ makes one of those direction
Mhm.
finding things like that. And then the
He
thing in your
actually-
car has an LED that circles, just like
Yeah,
the
yeah. That's what he
like the
had.
poorly produced movies, you know?
Mm-hmm. Yes, that's what he had, and he showed me that he was able to track down somebody. I thought that was amazing. That was so long ago. Yeah.
So
I don't know if you remember. I don't know if you remember back when the police used, I think it was called low jack antennas. You would see it a
Oh,
lot
yeah,
in Florida. They'd have the 4 antennas in the center roof of their car.
So what was that for? Just
For finding cars that had low jack direction
so that
finding.
was a system.
Right. You saw it a lot in Florida.
Oh, that's cool.
Yeah.
We
So-
used it up here too. If they went in and robbed a bank, there
Mhm.
would be a transmitter in the car, in the bag. They'd put it
Okay.
in the bag and then we'd track it down
Mhm.
with the directional antennas. Worked pretty good.
Wow,
And now they put a little GPS chip in the money if somebody tries to rob a bank. Mhm.
cool. So talking about that direction finding reminds me.
Yeah.
So our club up in Michigan, we used to do fox hunting every Wednesday night at 7 p.m. Everybody would meet in the parking lot, and we had remote foxes, 3 of them, and we turn them on with touchstones. And right at 7 o'clock, it was like that movie from the 70s or 60s, or that treasure movie where everybody took off and they're trying to find this treasure. I forget that name of that movie. And so everybody just ripped out of the parking lot trying to find this thing. And the guy I was with, we bought that MFJ direction finding thing at Dayton, and he had the 4 antennas, and it was going beep, 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 just like a poorly produced movie. And I'm in the passenger side watching this thing, and unbeknownst to me, while we were driving, and it looked like the signal's getting, hey, it's in that direction. We're driving, trying to find it, and it was getting weaker and weaker and weaker. And he says, what is going on? Because this guy I was with was very competitive.
It's moving. It's moving.
No, there's a
No?
switch on there to invert the signal. So we were actually driving away from the signal, exactly 180 degrees away from the signal.
Oh, interesting.
And I had bumped it with my thumb, and I didn't even know that switch was there.
Oh,
So we were driving away from the signal, exactly 180 degrees.
okay.
And he just lost it and was screaming and yelling at me, calling me names. So that was pretty funny. I guess he had to be there.
Yeah,
He used some other words too, but I don't want to repeat them.
no, you don't have to. Cool.
So that's pretty cool.
So, Paul, is this only used for receiving or can you transmit as well?
Well, I didn't want to talk about transmitting antennas for a couple reasons. The loop
Mhm.
antenna can be used for transmitting, but I didn't want to talk about them because I don't have any experience with those at all, because I don't have one. And also, I had to focus on one thing or the other, and the whole thing, how this all started, I was playing with a receive antenna. But you can transmit with loop antennas. You look at those antennas online, those loop antennas that transmit, and it's not a complete loop. Now, the receiving antennas I showed you, they're a complete dead short, right? It's a continuous connection from one end all the way around to the other side. So I look at it as a dead short. It's like putting a jumper on. Okay. Where the transmit antennas, well, yeah, the transmit antennas usually have a capacitor. So the inductor is made up by the loop itself. And then there's this capacitor that's in series. So the conductor or the inductor, which is the loop, and the capacitor is in series, creates a tuned circuit. So those are very selective, very high Q. You tune them for the exact frequency you're going to operate. And if you vary very far off of there, the SWR goes zoop, real high again. You got to retune them. And I guess those work pretty well. People have good luck with those.
Yeah, you have to get a high voltage capacitor, usually Soviet Union
Yeah.
capacitor. So,
So what happens
that's the
is-
problem with them.
Let me show you this picture because this is in my slide. And I'll just do a screen share this time. So, and then I'll just escape this here. Well, here, let me go back. So this is what they look like right here. This is a transmitting loop actually. So I used the wrong picture for this. But here's the transmitting loop. The coax is fed down here with a match, some sort of match. Just looks more like a gamma match type situation here. And there's the capacitor, which is 180 degrees or opposite of where the feed is. So when you look at this, exactly 180 degrees later, which is right across from the feed point, that's the high voltage node right here. So therefore, if you do put a capacitor in there, it has to be very high voltage capacitor, because if it's not, the plates will arc over. Now, if you use low power, you can get away with it. But if you use higher power, you got to have really widely spaced plates for your capacitor so it doesn't arc over. And that's a transmitting loop right there.
I got a question, Paul.
Okay.
You were saying that this is like a high Q tuned circuit.
Yeah.
Is that kind of like the theory in the duplexers?
Yeah. So what Q is referring to is quality. So when they say high Q or high quality, that means so you could have a high Q circuit and a low Q circuit. So a low Q circuit is a low quality circuit. So that's a circuit that is very broad banded.
Right.
So a low Q circuit is very broad banded. It'll cover a wide range of frequencies, but it's low Q, so it may not be as efficient. And then if you have a high Q signal or high Q filter or high Q antenna, whatever, that antenna is going to be very sharply tuned to one specific frequency, say for example, but it's going to be very efficient at that frequency that is tuned for. But then if you vary off of it very far, it goes out of tune very quickly. So if you use a high Q antenna for receiving, it'll receive great at 14.100. And then you start going down to 14.050 or, up to 150, you'll notice your receive sensitivity drops off almost right away. That's a good indication that's a high Q circuit.
Guys, I'm going to go back to bed. I'm going to disconnect here. I'm going to say thanks, Paul. It's interesting about the loop antenna. And I'll look at the video again. I'll look at the transmitting antenna. So thanks for the great presentation. I really enjoyed it.
All right. Thanks, Tom.
Night, Tom.
And before anybody else goes, I know we lost a few already. Next week, same time here on the same Zoom, same everything, 8 o'clock. John K2IZ going to be doing a presentation on the nano BNA, which should be very interesting too. Everybody, the $50 nano ANAs that I put mine up to a $30,000 analyzer, and it does about everything that the $30,000 analyzer does. You need to
Yes.
know how to use it, so we're all gonna learn next. There you go.
Uh-huh.
Joe's
I
got
got
one,
the
so that's,
nano. Yep.
that's next week, next Thursday, same time.
And I got the Spectrum.
Oh, cool.
Yeah.